A telescope just captured galaxies that should not exist. The James Webb Space Telescope looked 13.4 billion years into the past. It found galaxies so massive, they break every model of cosmic evolution. One galaxy contains as many stars as the Milky Way, but formed only 300 million years after the Big Bang. That is impossible, according to our current physics. These ancient galaxies are too bright, too organized, too mature. The universe did not have enough time to build them. Scientists thought the early cosmos was dark and chaotic. Webb revealed massive spiral structures and supermassive black holes where there should be nothing but hydrogen gas. The telescope keeps finding more of these cosmic impossibilities. Hundreds of galaxies that rewrote the textbooks. Each one forces us to reconsider the true scale of how fast the universe evolved. We thought we understood the growth timeline of everything. We were wrong by billions of years. The implications reach far beyond astronomy. If galaxies formed this quickly, our entire cosmological model needs rebuilding from the ground up. If you find this mind-bending, hit that like button and subscribe. We begin now. The astronomers staring at the data thought they had made a mistake. The numbers coming back from the James Webb Space Telescope did not make sense. They ran the calculations again. Same result. They checked the instruments. Everything working perfectly. The galaxy they were looking at had a redshift value of 14.32. That number told them something impossible. This galaxy existed just 290 million years after the Big Bang. Let me put that in perspective. The universe is 13.8 billion years old. This galaxy formed when the cosmos was less than 3% of its current age. 290 million years sounds like a long time until you realize what it means at cosmic scale. Picture waiting just 2 minutes after midnight on New Year's before checking what happened outside. You look out the window and discover someone built a fully furnished skyscraper. Foundation, steel frame, glass windows, electricity, plumbing. All of it constructed in 2 minutes. That is what this galaxy represents. They named it Jade's GSZ 140. The light reaching us now left that galaxy 13.5 billion years ago. When those photons began their journey toward Earth, there were no trees, no flowers, no animals, no fish, no insects, nothing alive anywhere that you would recognize as life. The photons hitting your eye when you look at this galaxy left before Earth had oxygen in its atmosphere, before complex life, before anything on our planet could breathe. You are not looking at a galaxy. You are looking at something older than respiration. Think about that. This is the part that gets me. These photons have been traveling longer than your species, your genus, your entire evolutionary family tree has existed, and they arrived just in time for you to look up. But here is what breaks everything we thought we knew. This galaxy is not just old. It is massive. It is bright. It has structure. Stars packed together in organized formations. Light pouring out at intensities that suggest billions of suns already burning. The galaxy glows with a luminosity that should not exist yet. According to every model of cosmic evolution, this is impossible. Not unlikely. Not unexpected. Impossible. The early universe was supposed to be dark, hydrogen gas floating in the void, tiny ripples of density gradually pulling together over hundreds of millions of years. The first stars should have been small. The first galaxies should have been dim, chaotic collections of a few thousand stars at most. Structure takes time to build. Gravity works slowly. You cannot rush the formation of something this complex. 290 million years is not enough time. The universe was still an infant, still cooling from the Big Bang, still settling into the physical laws that govern everything today. And yet, here sits this fully formed galaxy, shining brightly, organized, mature. Scientists expected to find faint smudges when they looked this far back, proto-galaxies, the messy ancestors of the structures we see today. Instead, they found Jade's GSZ 140. A galaxy that looks like it should exist billions of years later than it does. The problem is not that we cannot see it. The James Webb Space Telescope sees it perfectly. The problem is that it should not have had time to form yet. Every calculation says no. Every simulation shows this galaxy needs at least 500 million years to assemble itself. It existed in less than 300 million. The galaxy should not be there, not because it is too far away, because according to our physics, the universe had not existed long enough to build it. You are looking at an object that violates the timeline of creation itself. This is not a distant thing we are struggling to understand. This is an impossible thing. There is a difference. Distant just means far. Impossible means the rules we use to explain everything else do not work here. The brightness alone defies explanation. To shine that brightly, the galaxy needs billions of stars. To have billions of stars, it needs enormous clouds of gas collapsing into stellar nurseries. To have those clouds, it needs hundreds of millions of years of gravitational accumulation. It does not have that time. The universe was 290 million years old. That is barely a heartbeat in cosmic terms. And Jade's GSC 14-0 is not alone. Webb found more galaxies just like it, dozens of them, all existing in the first 500 million years after the Big Bang. All too bright, all too massive, all too structured, each one an impossibility stacked on top of the last. The theoretical models predicted darkness. Webb revealed light, lots of it. Cosmologists built their careers on understanding how galaxies form. Those models worked perfectly for the nearby universe. They explained spiral arms and elliptical shapes and the distribution of stars. They accounted for dark matter. They incorporated gravity, gas dynamics, star formation rates. Everything fit, until Webb looked backward in time and found galaxies that should not exist. This galaxy forces a question that echoes through every branch of cosmology. If the universe could build something this massive this quickly, what else did we get wrong about the beginning of everything? The timeline we trusted just collapsed. The formation models we relied on just failed. How did this happen? How does a galaxy beat the clock by hundreds of millions of years? How does structure emerge from chaos faster than physics allows? The answer is redshift. That's how we see the impossible. Light doesn't just travel through space. It travels through an expanding universe. The fabric of space itself stretches while light moves through it, pulling the light waves along with it. That stretching changes the light, makes it redder, makes it longer, makes it invisible to human eyes but perfectly visible to James Webb. This is the key to everything Webb discovered. When astronomers measure a galaxy's redshift, they're measuring how much the universe expanded since that light was emitted. The number they use is called Z. Jade's GSZ 14-0 has a redshift of Z equals 14.32. That means the universe expanded by a factor of 15.32 while that light traveled toward us. Redshift 14.32 means the light stretched like pulling taffy. Imagine stretching something the length of your thumb until it's as wide as a highway lane. That's how much the universe expanded while this light traveled. Every photon that left that galaxy started as ultraviolet or visible light, the kind of light your eyes could see. But after 13.5 billion years of traveling through expanding space, those photons stretched into infrared. They became invisible to us. Not because they disappeared, because they changed. The human eye sees wavelengths between 400 and 700 nanometers. That's the rainbow of visible light: red, orange, yellow, green, blue, violet. Webb sees wavelengths from 600 nanometers all the way to 28,000 nanometers. It looks past red into the deep infrared, into the part of the spectrum where ancient light ends up after being stretched across cosmic time. This is why Hubble couldn't find these early galaxies. Hubble looked primarily in visible light. The galaxies were there, the light was there, but it had shifted so far into infrared that Hubble was essentially blind to it. Like trying to hear a dog whistle. The sound exists. Your ears just can't detect it. Webb was built specifically to see infrared, not as a bonus feature, as its primary mission. Every component, every mirror coating, every instrument was designed to capture the stretched, ancient light from the universe's first galaxies. Webb is a time machine by design, not metaphor. That phrase gets used carelessly. Time machine. But in astronomy, It's literally true. Light travels at 186,282 miles per second. That speed is constant. It never changes. Distance equals time. When you look at something far away, you're looking at old light. There's no way around it. Look at the moon. You see it as it was 1.3 seconds ago. The light takes that long to reach you. Look at the sun. You see it as it was 8 minutes ago. Look at the nearest star beyond our sun. You see it as it was over 4 years ago. The farther you look, the deeper into the past you see. There is no such thing as seeing distant objects as they are now. It's physically impossible. This is the part that gets me. When you look at Jade's GSZ 14-0, you see a galaxy as it was 13.5 billion years ago. That's the only version of that galaxy you can ever see. What does that galaxy look like right now, today, 13.5 billion years after that light left? We will never know. We can never know. The light showing us its present won't arrive for another 13.5 billion years, long after our sun is dead. There is no present tense in astronomy. Every observation is archaeological. Looking at distant galaxies isn't like looking at faraway cities. It's like looking at old photographs. The farther the object, the older the photograph. That photograph is the only one that will ever reach us from that moment in time. Webb looks so far back that it sees galaxies from when the universe was less than 3% of its current age, less than 500 million years after the Big Bang. These aren't just distant galaxies, they're infant galaxies. Galaxies caught in the act of forming, or so we thought. The precision of Webb's instruments allows astronomers to measure redshift with extraordinary accuracy. They can determine not just that a galaxy is far away, but exactly how far, exactly how old the light is, exactly how much the universe expanded while that light traveled. These measurements aren't estimates. They're calculated from the spectrum of light itself. Different elements absorb and emit light at specific wavelengths. When those wavelengths shift, you can measure by how much. That tells you the redshift. The redshift tells you everything else. Webb's mirror is so smooth that if you scaled it up to the size of the United States, the tallest mountain on it would be 2 inches tall. That smoothness matters. Every imperfection scatters light. Every scatter loses information. Webb's mirror collects infrared light with almost no loss. It gathers photons that traveled for billions of years and focuses them precisely onto instruments that can read their stories. The telescope can detect a bumblebee on the moon. That's the sensitivity we're talking about. Not literally bumblebees, but the equivalent heat signature, the faint infrared glow. These early galaxies appear incredibly dim, not because they lack light, but because their light has been stretched thin across space and time. Finding them requires detecting whispers, faint signals buried in cosmic noise. Hubble saw the universe in visible light and some near infrared. It found galaxies out to redshift 11 or 12. Impressive, revolutionary for its time. But Webb sees deeper into infrared. It pushes past redshift 14, 15, even higher. Every unit of redshift is another step backward in time, another 100 million years closer to the beginning. That's how Webb revealed what Hubble couldn't, not by looking harder at the same wavelengths, by looking at different wavelengths entirely, by seeing the invisible made visible through the fundamental physics of cosmic expansion. The universe itself redshifted ancient light into Webb's view. All Webb had to do was look, the same patch of sky, the same tiny area Hubble looked at for days. The Hubble Deep Field showed us 10,000 galaxies, an achievement that revolutionized astronomy, a census of the distant universe. 10,000 island universes in a space no bigger than a grain of sand held at arm's length. Webb pointed at the same spot, the same coordinates, the same tiny window into deep space. It found 800,000 galaxies. 800,000 galaxies where we thought there were 10,000. Picture living in a town you thought had 10,000 people, then discovering the census missed 790,000 residents. They were there all along. You just couldn't see them, walking the same streets, living in houses you passed every day, invisible because you were looking with eyes that couldn't perceive them. That's what happened. The galaxies were always there. Hubble wasn't wrong. It was blind. We were all blind. Webb gave us new eyes. Think about what that multiplication means. If one tiny patch of sky holds 800,000 galaxies instead of 10,000, what does the entire sky hold? The observable universe stretches 93 billion light-years across, not 13.8 billion. That's just how long light has been traveling. The universe itself expanded while that light was in transit. Space stretched. The sources of that light moved farther away. The actual diameter of what we can observe, measured now, spans 93 billion light-years. Let me give you a sense of that timeline. If the universe's age were a 24-hour day, humans appeared in the last 4 seconds before midnight. Dinosaurs showed up 17 seconds ago. The Earth formed at 4 in the afternoon, and everything before 5 in the morning, just darkness and the first light. The cosmic dawn Webb is now revealing. Within that 93 billion light-year sphere, we estimate 2 trillion galaxies exist. 2 trillion. That's revised upward from the previous estimate of 200 billion. We were off by a factor of 10. The universe is 10 times more crowded than we thought. Each galaxy averages somewhere between 100 billion and 1 trillion stars. Let's take the larger number, 1 trillion stars in a single galaxy. Count 1 star per second. No breaks, no sleep, no stopping. It would take 1,688 years to count them all. You'd begin before agriculture was invented, before the first cities, before writing. You'd count through the entire span of human civilization and finish today. That's one galaxy. Webb sees 800,000 of them in one photograph. The numbers start to lose meaning. 2 trillion galaxies, each with hundreds of billions or trillions of stars. Multiply that out, and you get more stars in the observable universe than grains of sand on every beach on Earth. That comparison gets used often. It's overused because it's true, but even that doesn't capture it. Sand grains are finite. You could count them given enough time. The stars in the observable universe? You couldn't count them if you had 1 billion human lifetimes. Here's what changes everything. The universe appears to have no edge, no center. Every point looks like the center from its own perspective. An observer in a galaxy 10 billion light-years from us would see the same thing we see. Galaxies in all directions. A sphere of observable universe centered on them. Their 93 billion light-year bubble overlapping with ours. Both of us thinking we're looking at the whole picture. Both of us seeing only our local horizon. This is the part that gets me. The universe isn't mostly empty space between galaxies. It looks empty to us because we're looking with the wrong instruments. Hubble saw darkness between its 10,000 galaxies. Nothing visible, just gaps. We assumed those gaps were real, empty cosmic voids, the space between structures. Webb revealed what fills those gaps. Faint galaxies, distant galaxies, ancient galaxies we simply couldn't see before. The darkness was full, dense with light we couldn't detect. Every blank spot in Hubble's image contains dozens or hundreds of galaxies invisible to earlier technology. Emptiness was a limitation of our vision, not a feature of reality. The deep field images look crowded now, packed with galaxies overlapping each other, spirals and ellipticals and irregular shapes scattered across every pixel. No empty space remains. Point Webb anywhere, any random direction, and you'll see the same density. Thousands upon thousands of galaxies, each one a system of billions or trillions of stars, each one potentially hosting billions of planets. This isn't speculation. This is direct observation. We're not extrapolating from theory. We're counting what's actually there in the images. 800,000 galaxies in a patch of sky the size of a grain of sand. Scale that up to the full sky. Account for the regions we haven't observed in this detail yet, and you arrive at 2 trillion galaxies. Maybe more. The estimate keeps climbing as our instruments improve. What else are we missing? If we were wrong about emptiness, if we missed 790,000 galaxies in a single image, what else can't we see? Webb operates in infrared. It reveals galaxies hidden by redshift and dust. But there are wavelengths Webb doesn't observe. Radio waves, X-rays, gamma rays. Other instruments cover those ranges. Each one reveals structures invisible to the others. Each wavelength tells a different story. The universe isn't hiding from us on purpose. It's just vast, and we're only beginning to develop senses that match that vastness. We built eyes that see invisible light, then infrared, then radio. Each time we open a new window, we find a universe more complex than we imagined, more populated, more active, more real. You are here, on a rock, circling an ordinary star, in one galaxy, among 2 trillion. Each of those galaxies contains more stars than humans have drawn breaths in all of history, and we can see them now. We can photograph them, count them, study their light, measure their distances, read their compositions. They're not theoretical, they're real as the ground beneath your feet. 800,000 galaxies, one photograph, one tiny corner of endless sky. Just sit with that for a second. You can see 800,000 galaxies in one photograph. You know they're real because we just counted them. But there's a different question, a harder one. How do you actually build a machine that can see them? Not just see them as they were 13 billion years ago. See light so old it left its source before Earth existed, before the sun existed, before most of the universe looked anything like it does now. That's not a telescope problem. That's a time machine problem. The James Webb Space Telescope cost $10 billion, 25 years of development, thousands of engineers, all solving the same puzzle. How do you build an instrument sensitive enough to detect ancient light that's been traveling through expanding space for most of cosmic history? Every design choice is an answer to that question. Start with the mirror, 6.5 meters across. That's about 21 feet. Wider than a 2-story house is tall. It needs to be that large because ancient galaxies are faint, unimaginably faint. The bigger the mirror, the more light you collect. More light means you can see dimmer objects. Dimmer objects means you can see further back in time. But you can't launch a 21-foot mirror into space. It won't fit inside any rocket. So Webb's mirror isn't one piece. It's 18 hexagonal segments, each one made of beryllium, each one coated in gold. The gold isn't decorative. It's not about value or aesthetics. Gold reflects infrared light better than any other practical material. Silver would work better for visible light, but Webb doesn't look at visible light. It's an infrared specialist by design. Ancient light from the early universe has been stretched by cosmic expansion into infrared wavelengths. Webb's mirrors are giant gold eyes tuned specifically to see that stretched light. Those 18 segments launched, folded up, origami in reverse. They had to unfold in space, lock into position, then align so precisely that the entire mirror acts like a single perfect surface. The alignment tolerance is 1/10,000th the thickness of a human hair. If you scaled Webb's mirror to the width of the United States, any imperfection would be smaller than an ant. Think about that. 18 separate pieces, deployed in the vacuum of space, 1.5 million kilometers from Earth. No one can touch them. No one can fix them if something goes wrong. They have to be perfect on the first try. The mirror solves one problem. It collects faint light. But there's another problem. Heat. Everything warm emits infrared light. Your body does. Your phone does. The sun definitely does. If Webb's instruments are warm, they'll emit their own infrared glow. That glow would drown out the faint signals from distant galaxies. It would be like trying to see stars at noon with a floodlight pointed at your face. So Webb has to be cold. Not winter cold, not even space cold. -233 degrees Celsius. That's cold enough to freeze oxygen solid. Cold enough that air itself would fall to the ground as snow. That's where the sun shield comes in. 21 meters by 14 meters. About the size of a tennis court. 5 layers of material, each one thinner than a human hair. The side facing the sun reaches 85 degrees Celsius, hot enough to boil water. The side facing the instruments stays at -233 degrees. That's a temperature difference of 318 degrees across 5 sheets of film. The temperature difference across Webb's sun shield, one side hot enough to boil water, the other side cold enough to freeze oxygen solid, separated by 5 layers thinner than a human hair. The sun shield doesn't just block heat, It blocks light. The Sun, Earth, and Moon all stay on the same side, always. Webb operates in permanent shadow. Its instruments stay cold. Its infrared vision stays clear. But that creates a new problem. Where do you put a telescope that needs the Sun, Earth, and Moon to always be in the same direction? There's a spot, 1.5 million kilometers from Earth, about 4 times further than the Moon. At this location, the Sun's gravity and Earth's gravity balance perfectly. It's called the L2 Lagrange point. Picture a seesaw. 2 people of different weights sit on opposite ends. There's exactly one spot on that seesaw where both people could float, perfectly balanced. L2 is that spot. Webb sits in gravitational equilibrium. It uses almost no fuel to maintain position. It just hovers there, stable, quiet, cold. 1.5 million kilometers. That's far enough that if you pointed at Earth, your thumb would completely cover it. Far enough that radio signals take 5 seconds to arrive. Far enough that no human will ever visit to perform repairs. Webb is alone out there, permanently. It launched in December 2021. The launch was perfect. The deployment was perfect. 18 mirror segments unfolded. The sun shield unfurled. Every single mechanism worked. Any one of them failing would have ended the mission before it began. Then came alignment. 18 separate mirrors had to become one. Engineers sent commands. Tiny motors adjusted each segment, nanometers at a time. The mirrors shifted, tilted, curved, month after month of adjustments. Testing, refinement. By July 2022, the mirror was aligned. The instruments were calibrated. Webb was operational. 25 years of engineering, $10 billion, thousands of people, one telescope, sitting in the dark, 1.5 million kilometers from home, colder than anything natural has a right to be, watching the sky with 18 gold eyes. And then it started seeing things that shouldn't be there, things that don't fit the timeline we thought we understood. Galaxies so old and so bright, they seem to violate everything we know about how the universe grows. The telescope works exactly as designed, every mirror segment aligned, every system operational. The engineering solved the puzzle perfectly. What Webb found is a different puzzle entirely. Why do galaxies cluster in patterns instead of appearing randomly across space? Look at any map of the universe and you'll see structure, chains, filaments, walls of galaxies stretching across hundreds of millions of light years. Between them, vast empty regions. This isn't random. There's architecture here. Something organized all this matter into patterns before the first stars even turned on. The answer is dark matter. And we need to talk about what it does, not what it is. Dark matter makes up 85% of all matter in the universe. Everything we can see, everything made of atoms, stars, planets, gas, dust, you and me, all of it together is just 15%. We're the minority. The visible universe is the exception. Dark matter is the rule. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. The only way dark matter talks to normal matter is through gravity. That's it. One conversation, one force. But that single force shaped everything. Picture the universe a few 100 million years after the Big Bang. It's mostly hydrogen and helium, spread almost evenly through space. Almost, but not quite. There are tiny density variations. Regions where matter is slightly more concentrated. Dark matter responds to those variations immediately. It has mass, it has gravity, it clumps together. Normal matter wants to do the same thing, but it's held back. Gas bumps into itself. Atoms collide. Radiation pushes against it. Normal matter has friction. Dark matter doesn't. It moves freely. It collapses faster. It forms structure first. Those dark matter clumps grow. They pull more dark matter toward them through gravity. The concentrations get denser. Filaments start forming. Long chains of dark matter stretching across cosmic distances. The filaments connect. They intersect. They form a web. This happens while the universe is still mostly opaque, still thick with leftover radiation from the Big Bang. The scaffolding appears before anything visible can form. The frame goes up in the fog. Here's the part that matters. Normal matter, the stuff we're made of, can't ignore this structure. It flows along the dark matter filaments like water following riverbeds that were carved before the water arrived. Gas streams along these invisible channels. It accumulates where filaments intersect, where dark matter concentrations are strongest. That's where galaxies form. Not randomly, along the web, at the nodes, at the junctions where multiple filaments meet. Think of the cosmic web like soap bubbles in a sink. The bubbles are voids, empty and vast, while galaxies cluster in the thin films where bubbles meet. We live in the soap film, not the bubble. The largest structures in the universe, the superclusters and filaments we can map today, exist because dark matter built the framework first. Gravity did the rest. Let's talk about scale. Individual filaments of this cosmic web span hundreds of millions of light years. Light takes 500 million years to travel their length. If human civilization were a single frame in a movie, the filament would be a year-long film. Every frame of that film represents all of recorded history. Every empire, every discovery, every person who ever lived. The filament contains thousands of galaxies, billions of stars, and it's just one thread in a web that fills the observable universe. Between the filaments are voids, massive regions where almost nothing exists. These voids can be 500 million light-years across. You might think that's empty space. Actually, calling it empty space isn't quite right. Let me try again. It's empty of stars, of light, of anything we can see directly, but it's full of dark matter. The void isn't empty, it's invisible. Calling space between galaxy clusters empty is like calling a concert hall empty when the audience leaves, but the building's frame is still there. Dark matter is the frame. We just can't see it. The cosmic web structure we see today, this intricate pattern of filaments and voids, was already in place when the universe was less than 500 million years old. That's the surprise. That's what makes early galaxy formation possible and puzzling at the same time. The scaffolding existed before the buildings. Dark matter had already organized itself into this vast web while the first galaxies were just beginning to form. The architecture came first. The tenants moved in later. This matters for understanding what Webb is seeing. Those impossibly bright, impossibly organized early galaxies didn't form in random locations. They formed at the densest nodes of the dark matter web, places where multiple filaments converged, where gravity was strongest. The web channeled normal matter into those locations. Gas flowed, concentrated, collapsed, ignited. The web made galaxy formation faster and more efficient than it would have been in a smooth universe. But here's the tension. Even with the web in place, even with dark matter providing the gravitational scaffolding, those early galaxies are still too bright, too massive, too structured for their age. The web explains where they formed. It doesn't fully explain how they grew so large so fast. The framework was there. The construction happened faster than our models predict. Something accelerated the process beyond what dark matter's gravity alone should allow. The cosmic web spans scales almost too large to hold in your mind. A single filament, one thread in this universal tapestry, contains more galaxies than you could count in a lifetime. If you pointed at one galaxy per second, never sleeping, never stopping, it would take you thousands of years to count all the galaxies in just one filament. And there are millions of filaments. The web fills the entire observable universe, 93 billion light-years across, every region, every direction, all connected by dark matter we cannot see. We map this web by watching where galaxies are. We trace the visible matter and infer the invisible structure beneath it. It's like tracking an animal by its footprints. We never see the animal itself, just the marks it leaves behind. Dark matter is the animal. Galaxies are the tracks. The pattern is unmistakable, consistent. Everywhere we look, the same architecture appears. Filaments, nodes, voids, a web woven by gravity alone, holding everything together. This is the universe at its largest scale, not random, not uniform, structured by invisible matter into a web that channels visible matter into patterns. The web formed early. It shaped everything that came after. And somewhere along those ancient filaments, In the first few 100 million years, galaxies began turning on, lighting up the nodes, making the invisible framework visible for the first time. That's when Webb is looking. At the moment, the lights came on, at structures forming faster and brighter than the Webb alone should permit. The Webb shaped everything. It channeled matter into patterns. But how fast did this happen? How quickly is the universe still expanding today? That question has an answer. A number called the Hubble constant. It measures the speed of cosmic expansion. Every megaparsec of distance, the universe grows by a certain number of kilometers per second. Simple, clean, fundamental. Except we can't agree on what that number is. Two different methods measure the same thing. Both methods refined over decades by different teams. Both incredibly precise. Both confident. Both give different answers. Not slightly different, significantly different. The first method looks at the cosmic microwave background, the afterglow of the Big Bang itself, light from when the universe was 380,000 years old. Patterns in that ancient light encode information about expansion. Run the calculations. The answer comes out to 67.4 kilometers per second per megaparsec. That means for every 3.3 million light-years of space, the universe expands by 67.4 kilometers every second. A car moving at highway speed. The second method uses stars called Cepheid variables. They pulse at predictable rates. Brighter Cepheids pulse slower. Measure the pulse. You know the brightness. Compare that to how bright it looks. You know the distance. Use Cepheids to calibrate distances to supernovas. Use supernovas to measure expansion across billions of light-years. Run those calculations. The answer comes out to 73 kilometers per second per megaparsec. Same units, same measurement, different number. Imagine measuring your room with two rulers you built yourself using different methods. One ruler says the room is 100 feet long. The other says 107 feet. You check both rulers. They're built perfectly. You measure again. Same results. The room can't be both sizes, but both rulers are right. That's the Hubble tension. The difference matters more than you might think. If the cosmic microwave background measurement is correct, the universe is 13.8 billion years old. If the supernova measurement is correct, the universe is 12.8 billion years old. A billion years. That's not a rounding error. That's the entire span from single-celled life to humans. That's almost the age of Earth itself. One measurement says the universe has been expanding for 1 billion years longer than the other measurement allows. Scientists checked for errors. They rechecked. They refined both methods, built better instruments, collected more data, ran the numbers again. The discrepancy didn't shrink. It sharpened. As measurements got more precise, researchers expected the gap to close and disappear. Instead, it widened. Like focusing a blurry photograph and discovering the blur was hiding two completely different images. The statistical certainty that this discrepancy is real, not measurement error, sits at 5 sigma. That's the gold standard in physics, the same level of certainty scientists demanded before announcing the Higgs boson. 5 sigma means there's a 99.99994% chance this tension is real. The statistical certainty that this discrepancy is real is equivalent to the certainty that a coin flipped 14 times landing heads every single time isn't a fair coin. You could argue for luck once or twice, but 14 times? Something's wrong with the coin. Except here, both coins are perfect. Both methods work. We've tested them independently. The cosmic microwave background method traces expansion from the earliest moments of the universe. It looks at initial conditions and projects forward. The Cepheid and supernova method traces expansion from the present day. It looks at how fast distant galaxies recede right now and works backward. 2 different eras, 2 different approaches, same fundamental property, different answers. This is where the surprise lives. Better technology made this worse. When measurements have large uncertainty, discrepancies can hide in the error bars. As error bars shrink, the discrepancy should disappear if it's just noise. That's how science usually works. More precision means more agreement. Not here. Each improvement in measurement technique made both numbers more certain, made the gap between them more obvious. We're more confused now than we were with worse data. The better our instruments became, the deeper the crisis grew. The Hubble tension isn't some obscure technical problem. It suggests our model of the universe is incomplete. Something we don't understand is affecting expansion. Maybe the universe expanded differently in the past than it does now. Maybe dark energy isn't constant. Maybe there's something between us and the early universe we haven't accounted for. Or maybe both measurements are right, and the universe itself changed in a way we haven't predicted. Webb's observations feed directly into this tension. Those early galaxies forming too fast, too bright, too structured. They suggest the early universe was more active than our models allow. If expansion happened faster in certain periods, that could explain why galaxies assembled so quickly. It could also explain why our two measurements disagree. Different eras, different expansion rates, different physics. The ruler didn't break. The room changed size while we were measuring it. This is the uncomfortable place cosmology sits right now. We have two extraordinarily precise measurements of something fundamental. They disagree. We don't know why. The universe doesn't care what we find convenient. It doesn't have to follow our models. Our job is to figure out what it's actually doing. Right now, it's telling us we're missing something. Something big enough to change how we understand cosmic time itself. The Webb formed early. Galaxies lit up along its filaments. But the timeline for all of that depends on expansion rate. How fast was the universe growing when those first structures appeared? We thought we knew. We don't. And those impossible early galaxies Webb keeps finding, they're not just puzzles on their own. They're pieces of a larger crisis in how we measure cosmic history. The previous section left us with a crisis in cosmic measurement. The timeline of the early universe might be wrong. Those early galaxies, forming too fast, too bright, too structured, they appeared impossibly early. That raises a question we haven't addressed yet. Where did those galaxies get the materials to build stars in the first place? The Big Bang created hydrogen and helium. That's it. Some lithium, trace amounts of a few other light elements, but mostly just the two simplest atoms. Hydrogen made up about 75% of the early universe. Helium made up almost all the rest. Everything else came later. Everything heavier than helium had to be manufactured. But how? And where? The answer is inside stars. Specifically, inside the first stars. Stars we've never seen. Astronomers call them population 3 stars. The naming is backwards because we discovered stellar populations in reverse order. Population 1 stars are young, metal-rich stars like our Sun. Population 2 stars are older, with fewer heavy elements. Population 3 would be the first generation. Pure hydrogen and helium. No metals at all. In astronomy, metals means anything heavier than helium. Carbon is a metal. Oxygen is a metal. Iron, nitrogen, calcium. All metals in the astronomical sense. Population 3 stars had none of that. Just the primordial mix from the Big Bang. These stars were nothing like the Sun. They were massive. Current models predict masses between 100 and 1,000 times what our Sun weighs. A single population 3 star contained more mass than 500 suns. If you replaced our Sun with one, its surface would extend past Mercury's orbit. The inner planets would be inside the star itself. That much mass creates extraordinary pressure and temperature in the core. Population 3 stars burned furiously. They would have been 10,000 to 100,000 times brighter than the Sun. Beacons in the early cosmic dark, but their brightness came at a cost. They burned through their fuel fast. Population 3 stars lived for only 2 to 3 million years. They were born, fused hydrogen, created heavy elements, and exploded in less time than light takes to cross what would eventually become our solar system's diameter. Think about that timeline. 2 to 3 million years. That sounds long until you compare it to other stars. Our Sun has been burning for about 4.5 billion years. It'll keep burning for another 5 billion. Population 3 stars got a fraction of a percent of that lifespan. They lived fast. They died young. And when they died, they scattered their contents across space. Inside their cores, these massive stars fused hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon. The chain continued all the way up to iron. Each fusion step released energy. Each step required higher temperatures and pressures. The heaviest elements formed in the final moments before collapse. Then, the star exploded. A supernova. The blast wave carried those newly forged elements outward into the surrounding gas. Carbon, oxygen, nitrogen, iron, all the materials needed for rocky planets, all the materials needed for life. Every atom in your body heavier than helium was forged inside a massive star that died before the universe was even 500 million years old. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it came from stars you'll never see, stars that burned out billions of years before the sun ignited. Population 3 stars should have existed between 100 and 200 million years after the Big Bang. Right in the window, Webb is observing. We should be able to see them. Their light should be there, redshifted, but detectable. Webb is actively searching for their signatures. The problem is distinguishing individual population 3 stars from the early galaxies they formed inside. When you look at a distant galaxy, you're seeing the combined light of millions of stars. Picking out the signature of a single massive population 3 star in that mix is difficult. It's like trying to spot a specific bright light bulb in a stadium from 50 miles away. There are telltale signs we're looking for. Population 3 stars had no heavy elements to absorb specific wavelengths of light. Their spectra should be cleaner, simpler. They also produced enormous amounts of ultraviolet radiation. That radiation ionized the hydrogen around them, creating distinctive bubbles of ionized gas. Webb can detect those bubbles if they're there. The search continues. We haven't found definitive evidence yet. Here's what makes this uncomfortable. We teach population 3 stars as established fact. The textbooks say they existed. They say these stars were massive because the early universe lacked heavy elements. Without metals, gas clouds couldn't cool efficiently. They couldn't fragment into smaller pieces. So they collapsed into very massive stars instead. That's the standard explanation. But it's not entirely satisfying. We don't really know why the first stars were so massive. The textbook answer is that they couldn't fragment into smaller masses without heavy elements. But the physics of exactly why that is, the mechanism that prevents fragmentation, that's still being worked out. It's one of those things we teach as fact because it's probably true. But the honest answer is we haven't watched it happen. We have strong theoretical reasons to expect very massive first stars. Computer simulations support it. The logic makes sense. But we don't have direct observational evidence yet. We're looking for them with Webb. We haven't found them. That absence is itself interesting. Where are they? Did we miscalculate when they should have formed? Are they there but harder to detect than we thought? Or did something about the early universe prevent them from forming the way our models predict? Population 3 stars are the bridge between the primordial universe and everything that came after. They're the forges that created the periodic table. Without them, no rocky planets, no chemistry, no life. They made the universe interesting. The irony sits heavy. We exist because of these stars. The materials that make up your body, the planet you stand on, the device you're watching this on, all of it traced back to massive stars that lived and died in the cosmic dawn. We owe our existence to objects we've never directly observed. We're searching for our ancestors, giant stars that burned in an era when the universe was still young and simple. Stars that transformed that simplicity into complexity, into the rich chemical diversity we see today. Webb keeps peering deeper. Each observation captures light from earlier epochs. We're getting closer to the era when population 3 stars should appear. Maybe we've already seen them without recognizing their signature. Maybe they're hiding in data we haven't fully analyzed yet. Or maybe the first stars worked differently than we think. Maybe they were smaller, or rarer, or shorter-lived than our models allow. The universe has surprised us before. The galaxies Webb found forming too early might hold clues. If the early universe was more active than expected, maybe star formation happened differently. Maybe population 3 stars weren't the solitary giants we imagine. Maybe they formed in clusters. Or maybe heavy elements appeared faster than we think. cutting their era short. We're piecing together a story from fragments, distant light, theoretical physics, computer simulations. The story makes sense in outline. The details remain fuzzy. What we know for certain is that someone, somewhere, created the first heavy elements. Some process took pure hydrogen and helium and built carbon, oxygen, iron. That process almost certainly involved massive stars. Those stars almost certainly existed in the first few 100 million years after the Big Bang, and those stars almost certainly died violently, seeding space with the materials for everything that followed. We just haven't seen them yet. The first forges remain hidden, but we're looking. Remember that impossible galaxy from the beginning? Jade's GSZ14-0? It's not alone. It's not even the strangest one anymore. Webb keeps finding more. The crisis isn't one bad data point. It's a pattern. Jade's GSZ14-0 sits at a redshift of 14.32. That puts it 290 million years after the Big Bang, less than 300 million years. In cosmic terms, that's nothing. The universe was still an infant, and there it is, bright, structured, already packed with stars. But it has company. Webb found multiple other galaxies beyond redshift 10. That's the threshold, less than 500 million years after the beginning. These aren't faint smudges barely visible at the edge of detection. They're substantial, massive. According to our models, they shouldn't exist at all. Not yet. Not that big. Not that quickly. The structure formation timeline is scrambled. It's like planting an acorn and returning 2 weeks later to find a fully formed oak tree, complete with dense wood, thick bark, and a century's worth of growth rings. The growth should take time, lots of time. These galaxies skipped steps we thought were mandatory. Take the brightness of Jade's GSZ14-0 for its age. According to models, a galaxy that young should look like a candle flame. Instead, it's a stadium floodlight. The light output doesn't match. The mass estimates don't match. Nothing matches. Mass estimates exceed theoretical predictions by factors of 10 to 100. Not a little off, not within the margin of error, off by orders of magnitude. These galaxies contain as much mass as galaxies that should have taken billions of years to assemble. They did it in a few 100 million. Then there's the cosmic vine. This structure spans 13 million light years. 13 million. That's the distance light travels in 13 million years, moving at 671 million miles per hour, never slowing, never stopping. It's vast, and it contains several massive galaxies, all connected by filaments of gas and dark matter, all at a redshift of roughly 3.44. The universe was only 2 billion years old. The cosmic vine structure, multiple massive galaxies already connected by filaments, when the universe was only 2 billion years old, is like finding a major metropolitan area with highways and suburbs before you expected the first village. You don't build cities overnight. You don't connect them with infrastructure before you've established settlements. But there they are, connected, organized, already following the cosmic web we discussed earlier. These galaxies formed along dark matter filaments. That part makes sense. Dark matter provides the scaffolding. Gravity does its work. Matter flows along the densest paths. The cosmic web guides structure formation exactly as predicted, but the speed is all wrong. The timeline is compressed. What should take 5 billion years happened in 500 million. Every solution creates new problems. The cosmic web explains where these galaxies formed. It doesn't explain when or how fast. The models assume slow hierarchical growth. Small clumps merge into bigger clumps. Bigger clumps merge into galaxies. Galaxies merge into larger galaxies over billions of years. It's a gradual process, a patient process. The observations show rapid assembly, explosive growth. Something kicked structure formation into overdrive. Then there's the chemistry problem. These early galaxies already contain heavy elements: carbon, oxygen, nitrogen. We can see them in the spectra. The light carries signatures of elements that shouldn't exist yet. The Big Bang created hydrogen and helium. That's it. Everything else requires stars, fusion, nuclear reactions in stellar cores. And those stars need to die. They need to explode. They need to scatter their contents across space. That means population 3 stars not only existed, but already died and seeded the cosmos with heavy elements, all within the first 300 to 500 million years. The entire cycle happened. First star formation, fusion, supernova, dispersion, incorporation into second-generation stars. The full life cycle, complete, done. There's almost no time buffer between first stars form and complex galaxies exist. Think about that timeline. The universe begins. Hydrogen and helium cool enough to form structures. The first stars ignite. They burn through their fuel. They explode. Their remnants spread. New stars form from the enriched material. Those stars gather into galaxies. Those galaxies grow massive enough to be visible across cosmic time. All before the universe reaches its 500th millionth birthday. It's too fast. Every step should take longer. First, stars need time to form. They need time to burn. Even massive stars that die quickly still need millions of years. Supernovae need time to disperse their contents. New stars need time to condense from the enriched gas. Galaxies need time to assemble from those stars. Added up, the timeline doesn't fit. We expected a leisurely progression, a slow build from simplicity to complexity. The observations show a sprint. The early universe was active, violent, efficient. Structure formation happened on a deadline we didn't know existed. The models predict one thing, Webb shows another. Every galaxy that appears too early, too massive, too structured is another crack in the foundation. We can patch one crack, we can explain one anomaly, but this is systemic. The pattern holds across multiple discoveries, multiple redshifts, multiple independent observations. Either our distance measurements are wrong, which seems unlikely given how many independent methods confirm them, or our mass estimates are wrong, which also seems unlikely given how consistent they are, or our understanding of structure formation is wrong. That's the option nobody wants to face, but it's looking more likely every day. Galaxy formation should follow rules. Physics doesn't bend. Gravity works at a specific rate. Gas cools at predictable speeds. Stars form when conditions allow. You can't rush these processes. They're governed by fundamental forces. Yet somehow, the early universe rushed them anyway. We built our models carefully, decades of work, simulations that match the late universe beautifully. They predict how galaxies look today. They predict how they looked a few billion years ago. They even predict structures at moderate redshifts. But push back to the first billion years, and the models fall apart. The predictions diverge from reality, not slightly, dramatically. Maybe dark matter behaved differently in the early universe. Maybe it clumped faster. Maybe the filaments of the cosmic web were denser than we assume. That could accelerate structure formation, but it creates other problems. It requires dark matter physics we haven't observed. It requires properties we have no evidence for. Maybe the early universe was lumpier than we think. Maybe the initial density fluctuations were stronger. That would seed faster galaxy formation. But those fluctuations would leave signatures in the cosmic microwave background. We've measured that background precisely. The fluctuations match our models. They're not strong enough to explain what Webb sees. Maybe feedback processes worked differently. Maybe supernova winds and black hole jets didn't blow gas out of early galaxies as efficiently as they do now. That would let galaxies hold on to their material, grow faster, accumulate mass more quickly. But we don't know why feedback would be weaker. We don't have a mechanism. The universe doesn't care what we find convenient. It formed galaxies on its own schedule. Our models are approximations, useful fictions that capture the broad strokes. They were never perfect, but we thought they were close. We thought we understood the major processes. The discovery of multiple universe-breaker galaxies suggests we missed something fundamental. Maybe hierarchical assembly isn't the whole story. Maybe galaxies can form top-down under certain conditions. Maybe the early universe allowed formation mechanisms that don't work later. Maybe we're applying rules from the modern universe to an era when different rules applied. We're piecing together what happened from fragments of light, ancient photons that traveled for over 13 billion years, redshifted, stretched, faint. We're building theories from faint smudges on detectors, and those theories keep breaking. Every solution creates new questions. Every answer reveals deeper problems. The more we look, the less certain we become. Are our structure formation models fundamentally wrong? What if we tried to go there? What if we pointed ourselves toward Jade's GSZ 14.0 and just started moving? Let's start simple. Walking speed, 3 miles per hour, the pace of a casual stroll. If you started walking toward Jade's GSZ 14.0 right now, maintaining 3 miles per hour without ever stopping, no sleep, no death, just walking, the number of steps you would take exceeds the number of atoms in your body by a factor of several billion. You could disassemble yourself atom by atom with each step and still have steps left over. The distance is so vast that you as a physical object don't contain enough pieces to represent the journey. That's walking. What about driving? 60 miles per hour, highway speed, non-stop. You would be on the road for 340 quadrillion years. That's quadrillion with a Q, 340 followed by 15 zeros. Long enough that every star currently burning would have died. Their corpses would have cooled. The universe would have faded to darkness around you, and you would still be driving through the void. The road stretching ahead, empty, silent. All the light gone except your headlights. Maybe something faster. A commercial airplane, 500 miles per hour, cruising altitude maintained forever. The flight would last 41 quadrillion years. Longer than any physical structure could possibly survive. The airplane would decay around you. Its atoms would drift apart. The very concept of an airplane would cease to have meaning, and you'd still have most of the distance ahead of you. These numbers stop meaning anything. They're too big. They don't connect to human experience. Let's try the fastest thing we've ever built, the Parker Solar Probe, 430,000 miles per hour, the fastest spacecraft humans have ever launched. Point it at Jade's GSZ's 14.0 and never slow down. The journey would take 5.3 billion years. That's longer than the Earth has existed, longer than our sun has burned. You would leave before the solar system formed. You would pass through the entire history of our planet. The first cells, the first animals, the dinosaurs, their extinction, the ice ages, the first humans, all of civilization, and you would arrive just about now. 5 billion years of travel to cover 33.6 billion light years. The probe would be dust. Erosion from stray atoms in space would have worn it down to nothing. But imagine it somehow survived. Imagine you could look out the window. What would you see? Galaxies drifting past, red-shifted into invisibility as you left them behind. New galaxies ahead, blue-shifted as you approached. But mostly nothing. Void. Darkness so complete it has no reference point. You wouldn't see Jade's GSZ 14.0 getting closer. It's too faint, too far. You'd fly blind for billions of years. This is the fastest we can do, and it's not even close to fast enough. What about light itself? What if you could somehow travel at 670 million miles per hour, the absolute cosmic speed limit? Nothing moves faster. Nothing can move faster. The laws of physics forbid it. If you traveled at light speed, the fastest anything can possibly move, your journey would take 33.6 billion years. The universe itself is only 13.8 billion years old. You would need more than twice the entire age of all existence just to reach something we can see right now. You would need the universe to exist, to expand, to form galaxies and stars and planets, to do all that twice, and you still wouldn't be there yet. The universe hasn't been around long enough for light to make this trip, but there's something stranger, something that breaks the whole idea of traveling to distant galaxies. Even if you could travel at light speed, even if you had enough time, you can't reach these galaxies and see them as they are now. You can't catch up to the present moment. Picture it this way. You leave Earth today. You're traveling at light speed toward a galaxy 10 billion light years away. You arrive in 10 billion years. That's how long the journey takes for you. But time kept passing for the destination. That galaxy aged 10 billion years while you were traveling. You left to see it as it was 10 billion years ago, which is what we're seeing now. But you arrived 10 billion years in the future. You wanted to visit the past. You end up in the future. A future where that galaxy is unrecognizable, where its stars have evolved, where its structure has changed, where everything you wanted to see is gone. Every destination is stuck in the past relative to your departure point, and will be stuck in the future by the time you arrive. You can never catch up. You can never see the present moment of something far away. The distance guarantees you're always out of sync. There's worse news. Jade's GSC 140 isn't just 33.6 billion light-years away. It's also moving. The expansion of space is carrying it away from us. Right now, at this moment, the distance between us and that galaxy is increasing at roughly twice the speed of light. Not because the galaxy is moving through space that fast, because space itself is stretching, which means you can't reach it at all, not even at light speed. If you left right now, traveling at the speed of light, the galaxy would recede faster than you could approach. You would chase it forever. The distance would grow. Every second of your journey would take you further from your goal in absolute terms. You'd be running on a treadmill that's accelerating away from you, moving at the maximum possible speed, getting nowhere. The most distant galaxies we can see exist beyond what's called the cosmic event horizon, the boundary beyond which recession velocity exceeds light speed. We can see them because the light left before they crossed that boundary, but we can never reach them. They're visible but unreachable, observable but impossible. This is what distance means in an expanding universe. It's not like distance across a city. It's not fixed. The destination moves while you travel, and for the most distant objects, the destination moves faster than you can follow. The universe itself forbids the journey. Jade's GSC's 140 is right there. We have photographs. We can measure its properties. We can analyze its light, but we will never touch it, never send a probe to it, never see it up close. It exists only as light, ancient photons, information encoded in wavelengths. That's all we get. That's all we'll ever have. The scale isn't just big, it's insurmountable. There are places in the universe we can see but never visit. Galaxies that are real, physical, full of stars and worlds, but might as well be in another universe entirely for all the difference it makes. They're on the other side of a barrier that isn't made of matter or energy. It's made of distance and time and the expansion of space itself. We're not just far from Jade's GSC 140. We're separated by an impassable gulf. Looking at it isn't like looking at something across an ocean. It's like looking at something through a window that can never be opened. You can see through, but you can't reach through. The glass is space-time itself. Let's try something simple. Count with me. 1 star, 2 stars, 3 stars, 4. 1 number per second. You can do that. Anyone can do that. Keep going. 100, 1,000, 10,000. At 1 star per second, you'd count to 1,000,000 in about 11.5 days. No sleep, no breaks, just counting. You'd count to 1,000,000,000 in 31 years. Your entire adult life spent pointing at stars and saying numbers. The observable universe contains roughly 200 billion trillion stars. That's a 2 followed by 23 zeros. To count every star in the observable universe at 1 star per second would take 6 trillion years. If you started counting when the Big Bang happened and counted non-stop for the entire age of the universe, you would have counted about 0.0002% of all stars. You'd need 500 universe lifetimes to finish. You will never finish counting. Let's make it personal. You have a heartbeat. Right now, reading this, your heart is pumping. The average human experiences about 2.5 billion heartbeats in a lifetime. That's your entire existence measured in pulses. Birth to death. 2.5 billion moments your heart decided to keep going. If 1 star blinked out with every heartbeat, you would die having seen only 2.5 billion stars disappear. The Milky Way alone has 100 to 400 billion stars. Your entire lifetime of heartbeats would extinguish less than 1% of one galaxy out of 2 trillion. One galaxy. Less than 1%. And there are 2 trillion galaxies. The numbers don't just dwarf you, they erase you. Modern humans emerged about 300,000 years ago. That's every person who ever lived, every thought anyone ever had, every civilization that rose and fell. 300,000 years sounds like a lot until you hold it against cosmic time. Written history spans about 5,000 years. Everything we know about human achievement, every war and empire and discovery, fits into 5,000 years. The pyramids, Rome, the Renaissance, all of it. 5,000 years is 1.7% of human existence. And human existence is 0.002% of the age of the universe. We're not even a rounding error. Consider the light reaching us from Jade's GSC's 14.0. That light has been traveling for 13.5 billion years. When those photons left that galaxy, Earth was not even a speck of dust. Our sun didn't exist. The atoms that would eventually form you were scattered across space in different stars that hadn't died yet. That light is older than your planet's entire existence, by a margin of 9 billion years. 9 billion years before Earth even began to form, those photons were already halfway here. They were traveling toward a solar system that didn't exist yet, toward a planet that hadn't formed, toward a species that wouldn't evolve for billions of years. And they arrived right on time for you to see them. Think about the journey. That photon has been traveling for 97% of all time that has ever existed. If all of cosmic history is 100 seconds, that photon has been in transit for 97 of those seconds. It was born when the universe was barely 2% of its current age. From the photon's perspective, if it had one, almost nothing existed when it started its journey. No galaxies like ours. No stars like our sun. No rocky planets. All of that appeared along the way during its flight. The universe it left is not the universe it arrived in. And it doesn't care. The photon just travels 13.5 billion years at the speed of light without stopping, without slowing, without awareness. It crosses the entire observable universe and ends its journey by hitting a sensor on a telescope, transferring its energy, and ceasing to exist. 13.5 billion years of travel, one moment of detection, then gone. You only exist in the last fraction of that photon's story, the final page of a book billions of years long. By the time you arrived, the photon had already been traveling for longer than your planet would exist. You're not early to this story. You're almost too late. The scale isn't just big, it's definitional. It defines what matters and what doesn't. Your lifetime is about 80 years if you're lucky, 80 trips around the sun. In that time, light from the most distant galaxies will travel 80 light years closer to us. That's about 0.0000005% of the distance, essentially zero. In your entire life, the light from Jade's GSC's 14.0 will get 0.0000005% closer. You could live 1,000 lifetimes, and it would still be almost exactly as far away as it is right now. The universe operates on timescales that don't include you. Stars live for billions of years. Galaxies collide over hundreds of millions of years. The cosmic microwave background has been cooling for 13.8 billion years. And you get 80, maybe 90 if you're exceptionally lucky. You don't even get to see a single star complete its life cycle. Not one. The nearest star to us besides the Sun, Proxima Centauri, will live for about 4 trillion years. It's currently about 4.8 billion years old. You're witnessing 0.0000002% of its life, less than a blink. How do you make a galaxy that shouldn't exist? You don't. The math says it's impossible. The physics says there wasn't time. But there it is anyway. The universe doesn't care about our models. Jade's GSC's 14.0 formed when the universe was 300 million years old. That's early, impossibly early by our calculations. Galaxies that massive shouldn't exist yet. There wasn't enough time for that much matter to collect and collapse and ignite into stars. But it happened. The galaxy doesn't care that our equations say it can't be there. It formed anyway, and the light from that impossible galaxy has been traveling toward us ever since, for 13.5 billion years, crossing space that was expanding the entire time, moving through a universe that grew and stretched and changed completely while the photon just kept moving forward. And then it reached you. In your 80 years, in your 2.5 billion heartbeats, you happened to be standing on this planet, in this solar system, in this galaxy, at exactly the moment that photon arrived. You caught it, not personally, but your species built the telescope that did. After 300,000 years of human existence, you were here for the moment. We saw a galaxy that formed when the universe was barely out of infancy. That's not significance. That's coincidence. You're not special because you saw it. You're lucky. You're standing in the right place at the right time, in a universe so vast that right places and right times are almost impossibly rare. 200 billion trillion stars, 2 trillion galaxies, 13.8 billion years, and you get 80 years and 2.5 billion heartbeats to witness a tiny fraction of it. The numbers don't elevate you, they contextualize you. You are brief, singular, vanishingly small against the scale of everything, but you're here, right now, counting stars you'll never finish counting, watching light that's older than your planet, living a fragment of a cosmic second, and somehow, impossibly, aware of it all. How do we actually know what these distant galaxies are made of? We can't touch them, can't sample them, can't send a probe. They're billions of light years away. All we have is light, photons that crossed the universe to reach us. Everything we claim to know about these galaxies comes from reading that light, and the technique that lets us read it is called spectroscopy. Spectroscopy is the act of splitting light into its component wavelengths, like a prism breaking sunlight into a rainbow. But instead of just seeing colors, we see something far more revealing. We see gaps, dark lines where specific wavelengths are missing, bright lines where specific wavelengths shine stronger. These lines are fingerprints. Each element in the universe creates its own unique pattern. Spectroscopy is like listening to a choir singing. Even if you can't see the singers, you can identify individual voices by their pitch. Every element sings at its own frequency. Split the light, and you can hear which elements are singing. Here's how it works. When light passes through a cloud of gas, atoms in that cloud absorb specific wavelengths. The exact wavelengths depend on the element. Hydrogen absorbs light at very specific energies. So does oxygen, so does carbon. When you split the light into a spectrum, those absorbed wavelengths appear as dark lines. Absorption lines. The pattern of lines tells you which elements the light passed through. The reverse happens too. When atoms emit light, they do it at those same specific wavelengths. You get bright lines instead of dark ones. Emission lines. Same pattern, same fingerprint, just inverted. Think of absorption lines in a spectrum like grocery store barcodes. Each product has a unique pattern of black lines. In light from galaxies, each element creates its own barcode. Webb scans the barcode and identifies what the galaxy is made of. Hydrogen has one pattern, oxygen has another, carbon has another. The patterns never change. Hydrogen always absorbs light at the same wavelengths, anywhere in the universe, at any time in cosmic history. The laws of physics don't vary from place to place. Let's take hydrogen, the most abundant element in the universe. When an electron in a hydrogen atom drops from its second energy level to its first, it emits a photon with a wavelength of 121.6 nanometers. That's ultraviolet light, invisible to human eyes. We call this the Lyman alpha line. Every hydrogen atom does this, every single one. If you see that line in a spectrum, you know hydrogen is present. Oxygen creates multiple lines. One of the brightest appears at 500.7 nanometers. We call it oxygen 3, written in brackets with Roman numerals. That's visible light. Green, actually. When Webb looks at distant galaxies and sees this line, it knows oxygen is there, not just present. The brightness of the line tells us how much oxygen. The width of the line tells us how fast the gas is moving. One line, multiple pieces of information. Webb uses an instrument called NIR-SPEC, Near Infrared Spectrograph. It splits incoming light with incredible precision. The resolution ranges from about 1,000 to 3,000. That means if you're looking at a wavelength of 1000 nanometers, NIRSpec can distinguish features separated by as little as 0.3 to 0.1 nanometers. That's precise enough to identify individual elements, precise enough to measure their abundances, precise enough to see the differences between one galaxy and another. But here's where it gets complicated. These galaxies are ancient. Their light is severely redshifted. The wavelengths we observe aren't the wavelengths that were emitted. Everything has been stretched. Redshift stretches spectral lines like pulling a sound recording to play in slow motion. The pattern stays the same, but every frequency drops lower. A hydrogen line that should appear in ultraviolet gets stretched into visible light, then into infrared. Webb looks in infrared and finds the ancient patterns hiding there. That Lyman alpha line from hydrogen at 121.6 nanometers in the lab. But if you're looking at a galaxy with a redshift of 10, that line appears at 1337.6 nanometers. Infrared. The wavelength has been multiplied by 11. The pattern is preserved, just shifted. Webb knows what to look for. It finds the lines where they should be after accounting for redshift. Then it works backward to figure out which element created them. Every element has multiple lines. Hydrogen has the Lyman series. Oxygen has its forbidden lines. Carbon has its own set. Webb doesn't need to see all of them, just enough to make a positive identification. Once you identify one line from an element, you can predict where the others should appear. If they're there, you've confirmed it. If they're not, maybe that element is absent, or maybe it's too faint, or maybe the conditions in the galaxy don't produce those particular lines. The technique works because physics is universal. The same atomic structure that creates spectral lines on Earth creates them 13 billion light-years away. The same rules apply. The same energy levels. The same quantum mechanics. We can test this in labs. We know what every element's spectrum looks like. We've measured them all. When Webb sees those patterns in ancient galaxies, we know exactly what we're looking at. Here's the part that still surprises me. We don't just identify what elements are present. We measure the ratios. How much oxygen compared to carbon? How much carbon compared to nitrogen? How much nitrogen compared to iron? Those ratios tell us the entire history of star formation in that galaxy. Because different generations of stars produce elements in different proportions. The very first stars, population 3, created almost no iron. They fused hydrogen into helium into carbon and oxygen, some heavier elements, but very little iron. When those stars exploded, they seeded the universe with that specific chemical mix: high oxygen, high carbon, almost no iron. The next generation of stars formed from that enriched gas. They created more heavy elements, different ratios. By the third generation, you start seeing substantial iron. The proportions shift. We can determine not just what elements are in these early galaxies, but the ratio of elements, which tells us what generation of stars we're looking at. Population 3 stars create elements in specific ratios different from later stars. The chemical fingerprint is so precise that we can tell whether we're seeing first generation, second generation, or later stars based solely on the proportion of oxygen to carbon, to nitrogen to iron. Light doesn't just tell us what's there, it tells us the entire chemical history. When Webb looks at a galaxy from the early universe and measures low iron but high oxygen, that's a signature. Second generation stars. Population 3 already lived and died. Their remnants are there in the spectrum. We're seeing the aftermath, the chemical enrichment they left behind. We never saw population 3 directly, but we see their fingerprints in the composition of later stars. This is how we know those universe-breaker galaxies shouldn't exist. Not because we counted their stars. We can't resolve individual stars at that distance. But because we measured their spectra. We identified the elements. We measured the abundances. We determined the ages of their stellar populations based on which spectral features are present and which are absent. Young stars show different lines than old stars. Hot stars show different patterns than cool stars. The spectrum reveals it all. When Webb finds a galaxy that appears to have a stellar mass of 100 billion suns just 500 million years after the Big Bang, that mass estimate comes from spectroscopy. The brightness tells us how much light the galaxy produces. The spectrum tells us what kinds of stars are producing it. Hot, massive stars contribute more light per unit mass than cool, dim stars. By analyzing the spectrum, we calculate how much stellar mass is needed to produce that light. That's where the mass number comes from. Not guesswork, measurement. Same with stellar ages. Old stars have different chemical compositions than young stars. Old stars formed from gas that was already enriched with heavy elements from previous generations. Young stars formed from more pristine material. The presence of certain elements and their ratios tells us how old the stellar population is. When we say a galaxy contains stars that are 400 million years old, we're reading that from the spectrum. The light carries the timestamp. Every claim about these distant galaxies rests on this technique. When we say a galaxy is metal poor, we measured the metal lines and found them weak. When we say a galaxy is forming stars rapidly, we saw strong emission lines from ionized gas. When we say a galaxy contains dust, we saw the continuum spectrum reddened by absorption. The spectrum is the evidence, not circumstantial, direct. This is what separates modern astronomy from ancient stargazing. We're not just observing, we're analyzing. Every photon carries information encoded in its wavelength. Webb catches those photons, splits them, measures them, and extracts meaning from patterns of light and dark. We're 13 billion light-years away from these galaxies, but we know their composition, their temperature, their motion, their history, all from light, just light. Nothing else reaches us. But light is enough. The universe-breaker galaxies aren't alone. They're not outliers. They're not measurement errors that will disappear with better calibration. They're part of a pattern, and the pattern is showing up everywhere Webb looks. Start with black holes, supermassive ones, the kind that anchor the centers of large galaxies. Webb has detected black holes with masses between 10 million and 100 million times the mass of our Sun. That's not unusual. What's unusual is when these black holes existed, less than 500 million years after the Big Bang, at redshifts greater than 10, when the universe was still in its infancy. Here's the problem. Black holes form when massive stars collapse. A star, maybe 20 times the Sun's mass, dies and leaves behind a black hole maybe 10 times the Sun's mass. Then, that black hole grows by feeding on surrounding gas and merging with other black holes. This process takes time, a lot of time. To build a black hole with 100 million solar masses through standard processes requires billions of years of steady feeding and countless mergers. The universe at 500 million years old didn't have billions of years. It barely had 500 million. Finding supermassive black holes in the early universe is like discovering a 200-year-old oak tree on an island that emerged from the ocean last week. There simply wasn't time for normal growth. Something else happened. Either black holes formed much more massive than we thought possible, or they grew far faster than our physics allows, or they were seeded by some process we haven't identified. None of these options fit the standard model. That's one pattern. Here's another. Webb detected organic molecules in galaxies at redshift around 6. The universe at that point was less than 1 billion years old. These aren't simple molecules. They're polycyclic aromatic hydrocarbons, PAHs, ring structures made of carbon and hydrogen, the chemical building blocks that lead to things like sugars and amino acids. Complex chemistry, the kind that requires multiple generations of stars to produce the necessary elements, then specific conditions to assemble those elements into intricate molecular structures. It's like finding a fully stocked chemistry lab in a building where the foundation was poured yesterday. The materials shouldn't exist yet. The processes that create them need time to unfold. Stars must form, live their lives, explode, scatter heavy elements, allow new stars to form from enriched gas, create the right environments for molecule formation. This chain of events was supposed to take several billion years. Webb sees it completed in under 1 billion. The early universe was making complex chemistry faster than our models predict. Then there's structure, galaxy morphology. Webb is observing spiral galaxies with well-defined arms and central bars at redshift greater than 3. The universe at that epoch was less than 2 billion years old. Spiral structure requires organization. Density waves propagating through a rotating disk. Stable dynamics. Time for gravitational interactions to settle into ordered patterns. The expectation was that early galaxies would be irregular, clumpy, chaotic. Small galaxies merging and colliding, creating messy structures that only gradually organized into the elegant spirals and ellipticals we see in the nearby universe. This maturation process was supposed to take many billions of years. You form a galaxy, it starts out disordered, interactions and mergers eventually shape it into something structured. Webb seeing spiral galaxies with clear structure in the early universe overturns that expectation. It's like expecting caterpillars and finding butterflies already flying. The transformation happened faster than the models allowed. Every direction Webb points, it finds maturity, order, complexity, things that should take billions of years to develop, already present when the universe was young. I think about this sometimes. The crisis in cosmology didn't start with one impossible galaxy. It started because a telescope worked too well. Webb was supposed to confirm our models with better data. Instead, it revealed the models were incomplete. Better observations don't always mean clearer answers. Sometimes they mean better questions. The pattern across all these discoveries isn't just that things are bigger than expected. It's that the early universe was more organized than expected. Structure, chemistry, complexity all appear with shocking speed. The standard model predicted a messy, chaotic early universe that slowly organized over billions of years. A gradual process, simple to complex, disordered to ordered. Webb reveals an early universe that hit the ground running, organized, structured, chemically complex within a few 100 million years. Galaxies with billions of solar masses already assembled. Black holes with masses that should require billions of years of growth. Organic molecules that need multiple stellar generations to form. Spiral arms that require stable dynamics and time to emerge. This changes the picture fundamentally. The universe didn't stumble out of the Big Bang and gradually find its footing. It exploded into existence and immediately started building complicated structures. Consider what this means. The processes that form galaxies, grow black holes, create complex chemistry, and organize structure were all far more efficient in the early universe than we thought possible, or they operated under different conditions that we don't yet understand, or our entire framework for how structure forms is missing something crucial. The crisis isn't one measurement. It's that every measurement shows more order, faster than theories predicted. Each new observation from Webb reinforces the same conclusion. The early universe was not the simple, slowly evolving place we modeled. It was dynamic, fast, organized from the start. This isn't something you can fix with small adjustments. You can't tweak a parameter here or revise a calculation there and make this go away. When every observation points in the same direction, when the pattern holds across black holes, chemistry, and structure, you're not looking at measurement error. You're looking at a paradigm problem. Something fundamental about our understanding of how the universe forms structure is incomplete. Maybe dark matter behaves differently in the early universe. Maybe the initial density fluctuations from the Big Bang were larger than we thought. Maybe feedback processes that regulate star formation worked differently when the universe was young. Maybe there are physics we haven't accounted for. The weight of evidence is accumulating. Each new Webb observation adds another piece that doesn't fit. Universe-breaker galaxies were just the beginning. They were the first signal that something was wrong. But they're not alone. They're part of a broader story. A story about an early universe that refuses to match our predictions. And we're still at the start of Webb's mission. The telescope has years of operation ahead, more observations, deeper looks, wider surveys. Every time Webb peers into the early universe, it finds something that challenges expectations. The question isn't whether our models need revision. The question is how deep that revision needs to go. The previous section left us staring at an early universe that won't behave. Galaxies forming too fast, black holes growing too large, structure appearing when it shouldn't exist. But here's a different kind of problem. One that comes from the opposite direction. Not from things appearing too early, but from there being too many places for things to appear at all. Recent observations have forced a revision. The Webb telescope, combined with data from the WMAP and Planck satellites, has pushed the estimated number of planets in the observable universe upward, way upward. Previous estimates hovered around a few hundred quintillion. The new number is 4,000 quintillion planets. That's 4 times 10 to the 21st power. 4 followed by 21 zeros. The playing field just got an order of magnitude larger than we thought. 4,000 quintillion planets. Let's sit with that number for a second. If you counted 1 planet per second, never stopping, never sleeping, it would take you 126 billion years to count them all. That's 9 times longer than the universe has existed. You'd need 9 complete universes worth of time just to count the planets in this one. And we're still finding more. This number changes the conversation about life in the universe. Not whether it exists. Whether we're alone becomes almost absurd when you're talking about 4,000 quintillion chances. The math overwhelms intuition. Even if the odds of life developing are spectacularly, ridiculously low, the sheer number of opportunities makes it almost certain that life exists somewhere else. Probably many somewheres. Think about it this way. 4,000 quintillion planets. If only 1 in every trillion planets develops life, that's still 4 million planets with life. If only 1 in every million of those develops technological civilization, that's still 4 civilizations per galaxy. The numbers are so vast that even absurdly pessimistic estimates still yield a universe full of life. You can make the odds as long as you want. The number of planets is bigger. This is what the Drake equation has been trying to tell us for decades. The equation breaks the question down into factors. What fraction of stars have planets? We know now, nearly all of them. That fraction is essentially 1.0. What fraction of those planets are in the habitable zone? Observations suggest about 20%, maybe 1 in 5. What fraction of those develop life? Unknown. What fraction develop intelligence? Unknown. What fraction develop detectable technology? Also unknown. But here's the thing, those unknown factors can be incredibly small, and the equation still spits out large numbers, because you're multiplying small fractions by 4,000 quintillion. Even conservative estimates that assume life is rare and intelligence rarer still, suggest thousands to millions of technological civilizations in the observable universe. The uncertainty isn't whether they exist. The uncertainty is how many. Statistical probability makes alien life nearly certain. The universe is too big and too full of planets for Earth to be unique. Somewhere out there, on a planet orbiting a star we've never seen, in a galaxy whose light is just now reaching us, something is alive. Maybe something is thinking. Maybe something is looking up at their sky and wondering the same thing we're wondering. The math says yes. The numbers make it almost impossible to say no, but there's a problem, a big one, and it has nothing to do with probability. It has everything to do with distance. The nearest potentially habitable exoplanet we know about is Proxima Centauri b. It orbits a red dwarf star 4.24 light-years away. That's the closest one. Light takes 4.24 years to get there. A radio signal traveling at light speed takes the same time. 4.24 years from transmission to arrival. If we sent a message today and they responded immediately, we'd hear back in 8.5 years. Hello, 8 years pass. Hello back. That's the nearest star system. One exchange takes nearly a decade. A conversation is impossible. You could send a question and die of old age before the answer returns. And that's our closest neighbor. That's the best case scenario. Most potentially habitable planets are hundreds or thousands of light years away. A message to a civilization 1,000 light years distant would take 2,000 years for one exchange. You send a greeting in the year 1000. They receive it in the year 2000. They respond immediately. You get the response in the year 3000. Your civilization might not exist anymore. For a civilization in another galaxy, the delay is millions to billions of years. The Andromeda galaxy is 2.5 million light years away. A message sent to Andromeda today would arrive in 2.5 million years. If they responded instantly, we'd hear back in 5 million years. Humans as a species have only existed for about 300,000 years. You could send a message and receive a reply after your species has gone extinct, after your entire evolutionary lineage has diverged into something unrecognizable. The universe isn't just big, it's so big that communication across it becomes meaningless. Physics doesn't just make contact difficult, it makes contact functionally impossible. Nothing travels faster than light. That's not a technological limitation, that's a law of the universe, which means the speed of communication has a hard limit, and the distances are so vast that even at that maximum speed, messages take epochs to arrive. We're like people living on separate islands in an ocean so vast that no boat could ever cross it. No signal could ever reach shore. To shore, each island convinced the others must exist, but forever unable to confirm it. The isolation isn't because the islands are rare, it's because the ocean is too big. There could be thousands of other islands, millions of other people, entire civilizations on distant shores, but the distance makes them irrelevant. You can know they're probably out there. You can do the math. You can look at the number of islands and calculate that statistically you can't be alone. But you'll never see them, never speak to them, never confirm they exist. This is where the question shifts. It's not, are we alone? It's, are we permanently isolated? And the answer to that second question is almost certainly yes. Even if the galaxy is full of life, even if every 10th star system has a planet with something living on it, the distances are too great. The timescales are too long. We exist in a universe where alien life is probable, but alien contact is impossible. Not unlikely, impossible. The crisis isn't scarcity of opportunity. The universe has provided 4,000 quintillion chances for life to develop. That's abundance. Overwhelming, ridiculous abundance. The crisis is abundance of isolation. All those planets, all those potential homes for life spread across distances so immense that they might as well not exist, separated by voids that no signal can cross in any time frame that matters to a biological organism, to a civilization with a limited lifespan, to anything that experiences time the way we do. Every telescope that looks deeper doesn't make the universe seem emptier. Webb has shown us that. It reveals more galaxies, more stars, more planets, more places where life could exist. The revelation isn't that we're alone, it's that we might be surrounded by life we'll never meet, by civilizations we'll never contact, by neighbors we'll never know. The universe is full, but the universe is also so big that full and empty feel the same. And this isolation? It's not static, it's getting worse. And this isolation? It's not static, it's getting worse. If gravity attracts, why doesn't the universe's expansion slow down? That's what scientists assumed for decades. Expansion started with the Big Bang. Gravity pulls everything together, so expansion should slow over time, like throwing a ball into the air. It goes up fast at first, then slows, then eventually falls back down. The universe should behave the same way. In 1998, 2 teams of astronomers pointed their telescopes at distant supernovae, type Ia supernovae specifically. These exploding stars have a known brightness. You can measure how far away they are by how dim they appear. It's a cosmic yardstick, reliable, tested. They found something that made no sense. The distant supernovae were dimmer than expected. That meant they were farther away than they should be. The universe hadn't been slowing down. It had been speeding up. Expansion was accelerating. Dark energy is like throwing a ball upward and watching it slow down as expected, then suddenly watching it accelerate upward instead, moving faster and faster away from you despite gravity trying to pull it back. The universe isn't just expanding, it's expanding faster as time passes. 3 scientists won the Nobel Prize in 2011 for this discovery: Saul Perlmutter, Brian Schmidt, Adam Rees. They revealed that something is pushing the universe apart, something we can't see, can't touch, can't explain. We call it dark energy because we have no idea what it actually is, which is a fancy way of saying we have no idea. Dark energy makes up 68% of the universe's total energy. Not 68% of the matter, 68% of everything. The stuff we can see, the stars and galaxies and planets, that's less than 5%. Dark matter is about 27%, and dark energy is the rest. Most of the universe is this invisible force pushing everything apart. The expansion rate right now is about 70 kilometers per second per megaparsec. That's a mouthful. Here's what it means. Take a galaxy 1 megaparsec away. That's about 3.3 million light years. That galaxy is moving away from us at 70 kilometers per second. Not because it's traveling through space, because space itself is expanding between us and that galaxy. Now take a galaxy twice as far, 2 megaparsecs. It's receding at 140 kilometers per second. 3 megaparsec, 210 kilometers per second. The farther away something is, the faster it recedes. Galaxies beyond a certain distance recede faster than the speed of light. That sounds impossible. Nothing can move through space faster than light, but space itself has no speed limit. Space can expand as fast as it wants. Those distant galaxies aren't moving. The space between us and them is growing. Every second, 22,000 cubic miles of new space appears between us and distant galaxies. 22,000 cubic miles. That's larger than Lake Superior. Imagine an empty volume larger than Lake Superior materializing from nothing every single second, forever. You can't stop it. You can't slow it. It just keeps appearing. This is where the isolation becomes permanent. Remember those galaxies we can't reach because they're too far away? The ones where even light speed travel wouldn't get us there in time? Dark energy makes that problem worse. Much worse. Those galaxies aren't just unreachable. They're accelerating away from us. The gap is widening faster as time passes. Galaxies that are currently visible, that we can see with Webb, will eventually redshift beyond detectability. Their light will stretch so much it becomes invisible, undetectable, as if they never existed. The observable universe will shrink, not because anything is moving toward us. The universe keeps expanding, but distant objects will be receding so fast their light can never reach us. It's like standing on a shore, watching islands sink below the horizon, except the islands aren't sinking. The ocean is growing between you faster than you can cross it. The islands are still there. You just can't see them anymore, can't reach them, can't prove they exist. In trillions of years, only local group galaxies will remain visible. That's the Milky Way, Andromeda, Triangulum, maybe 30 or 40 smaller galaxies bound together by gravity. Everything else will have accelerated beyond the horizon. The rest of the universe, all those billions of galaxies Webb has revealed, will be invisible, unreachable, gone from view. Civilizations that arise trillions of years from now will look at the night sky and see almost nothing. A few nearby galaxies. That's it. They'll have no evidence that the rest of the universe exists. No distant galaxies to study. No cosmic microwave background to measure. No way to know the universe had a beginning. They'll think their local group is the entire cosmos. They'll be wrong, but they'll have no way to discover the truth. We exist in a cosmic moment where the distant universe is still visible. Barely. Webb can see galaxies forming 13 billion years ago. We can measure the cosmic microwave background. We can trace the universe back to the Big Bang. We have evidence. Future civilizations won't. They'll live in the same universe we do. But from their perspective, it will look empty, silent, small. This is the part that gets me. The universe isn't just big. It's not just expanding. It's erasing its own history. Dark energy is wiping away the evidence that there ever was a Big Bang, that there ever were distant galaxies, that the universe is anything more than a small cluster of stars in an infinite void. The truth will still be true, but it will become unprovable. The isolation described in the previous section, the idea that we might be surrounded by life we'll never contact, that's bad enough. But dark energy makes it terminal. Those civilizations that might exist on distant planets, they're not just too far to reach. They're accelerating away. Every second, the gap grows. Every second, contact becomes more impossible. Not less. More. And it's accelerating. The universe's future is lonelier than its present. We can see distant galaxies now. In 1,000,000,000,000 years, they'll be gone from view. In 10 trillion years, almost everything will be invisible. The cosmos will appear empty from within, isolated islands of matter surrounded by endless, unreachable darkness. Each island unaware the others exist, each one alone. You might think isolation is a fixed state. You're either isolated or you're not, but dark energy changes that. Isolation is a process. It's happening right now. Galaxies visible today will be invisible tomorrow. Not metaphorical tomorrow, actual tomorrow, measured in cosmic time. The universe is pulling itself apart, and the rate at which it's pulling apart is increasing. We are living in the only era when the full universe is visible, when evidence of the Big Bang still exists, when the cosmic web of galaxies can still be mapped, when the true scale of everything can still be measured. This moment, right now, is as connected as the universe will ever be. From here, it's all separation, all acceleration, all exile, and there's nothing we can do to stop it. We discovered the universe doesn't care about us gradually, one wound at a time. 1543, Nicholas Copernicus publishes his model of the solar system. Earth orbits the sun. We're not at the center. That was the first demotion. For thousands of years, humanity believed everything revolved around us. Literally, the planets, the sun, the stars, all spinning around Earth like we were the pivot point of creation. Then Copernicus showed the math only worked if we were moving, if we were just another planet, if we weren't special. People resisted, churches condemned it, scholars mocked it, because it hurt. Being displaced from the center of everything felt like losing something fundamental about who we were. But it was true, and truth doesn't care about feelings. 1920, Harlow Shapley maps the Milky Way. He measures distances to globular clusters, those ancient spheres of stars that orbit our galaxy. He expects to find the sun near the center. That's where we should be, right? If we're not at the center of the solar system, at least we're at the center of our galaxy. We're not. The sun sits about 26,000 light years from the galactic core. That's 2/3 of the way out. We're in the outer suburbs, the cosmic equivalent of a strip mall next to a highway exit. Nothing particularly central, nothing particularly special. Second demotion, 1929. Edwin Hubble turns his telescope on fuzzy patches of light called nebula. Some astronomers think they're clouds of gas inside our galaxy. Hubble measures their distances. Turns out they're not inside our galaxy at all. They're other galaxies, millions of light years away, entire island universes, each containing hundreds of billions of stars. The Milky Way isn't unique. It's one galaxy among countless others. We're not at the center of the universe because the universe has no center. Every point in space sees the same thing. Galaxies in all directions, receding in all directions, with no special location anywhere. Third demotion. This pattern has a name, the Copernican principle. It states that we don't occupy a special position in the universe, not in space, not in time, not in composition. Everywhere we look, we're typical, average, one of many. Every major astronomical discovery follows the same pattern. We thought we were central, special, unique. Then we discovered we're one of many, typical, average. We've been demoted from the center of creation to the outer suburbs of an ordinary galaxy in an ordinary region of space containing nothing particularly special. The Copernican wound keeps reopening. Each time we think we've found something unique about our situation, we discover it's common. Earth seemed special until we found exoplanets everywhere, thousands of them, tens of thousands. The sun seemed special until we catalogued trillions like it. Even our galaxy seemed special until Webb revealed 800,000 galaxies where we thought there were 10,000. We keep finding out we're less unique than we believed. Even our composition isn't special. Dark energy makes up 68% of everything. Dark matter makes up 27%. Normal matter, the stuff we're made of, makes up about 5%. We named the 68% dark energy because we genuinely have no idea what it is. Very scientific, very honest. We're made of the minority ingredient in a universe mostly composed of things we can't see and don't understand. We're not even made of the majority ingredient. The numbers now are staggering. 2 trillion galaxies in the observable universe, each one containing an average of 100 billion stars. That gives us roughly 200 billion trillion stars. If even a tenth of those stars have planets, and even a tenth of those planets sit in the habitable zone, we're looking at something like 4,000 quintillion potentially Earth-like worlds. 4,000 quintillion. That's 4 followed by 21 zeros. Write it out and it looks absurd. We're not special. We're statistically guaranteed to be common. Here's what most people don't realize. The Copernican principle isn't just historical fact. It's a predictive tool. When astronomers assume we're not special, they make better predictions than when they assume we are special. The assumption of mediocrity has been more scientifically productive than the assumption of significance. Think about how strange that is. Scientists get more accurate results when they assume humanity has no privileged position. When they design cosmological models, they start with the premise that the universe looks roughly the same from every vantage point, homogeneous and isotropic. That's the cosmological principle, and it's an extension of Copernicus. It says there's nothing special about our location in space or time, and it works. Models based on the cosmological principle accurately predict the cosmic microwave background. They predict the distribution of galaxies. They predict the rate of expansion. Being average isn't a philosophical stance. It's a methodology that generates accurate models. Our lack of importance is useful, scientifically useful. You might think that's depressing, that discovering we're ordinary diminishes us somehow. But consider the alternative. If we were special, if Earth occupied some unique position, that would mean the laws of physics might be different elsewhere. It would mean our observations couldn't tell us about the broader universe. It would mean we were fundamentally alone in a way that made understanding anything beyond our immediate vicinity impossible. Being typical means the universe is comprehensible. It means what we learn here applies there. It means the chemistry that produces life on Earth could produce life elsewhere. It means we're part of a cosmos that follows consistent rules, not isolated in a bubble of special conditions. Mediocrity connects us. Uniqueness would isolate us. Webb just extended this pattern. Those early galaxies, forming 300 million years after the Big Bang, they're not special. They're everywhere. That means galaxy formation wasn't a rare event requiring precise conditions. It was common, inevitable. The universe makes galaxies the way Earth makes clouds, constantly, everywhere, under a wide range of conditions. The exoplanets Webb is studying, their atmospheres contain water vapor, carbon dioxide, methane, the same molecules we have here, the same chemistry, the same building blocks. We're not made of rare materials assembled in a unique configuration. We're made of common ingredients following predictable patterns. Even the cosmic web, that vast network of filaments and voids that connects galaxy clusters across billions of light years, looks the same in every direction. There's no edge, no center, no special axis, just structure repeating at every scale, following the same rules, exhibiting the same patterns. We've looked at the universe from our tiny vantage point and found it looks exactly how it should look if we're not special, if we're just one observation point among countless possible observation points. If our galaxy, our star, our planet, our existence are all typical examples of common phenomena, the wound keeps reopening because we keep looking. And every time we look deeper, we find more places like home, more stars like ours, more galaxies like ours, more evidence that we're average. Some people find that lonely, all those worlds out there, and we're nothing unique among them. But there's another way to see it. We're connected, made of the same matter, following the same physics, part of a universe that's comprehensible precisely because it doesn't make exceptions. We're not the center. We're not special. We're not unique. We're one data point in a universe containing trillions of data points just like us. And that pattern, that repetition, that cosmic democracy of ordinariness is what makes the universe knowable. It's what lets us look 13 billion years into the past and understand what we're seeing, because the rules there are the same as the rules here, because we're typical, because the universe doesn't care enough about us to make us an exception. The observable universe has a radius of 46.5 billion light years. That's the current proper distance to the farthest point from which light has had time to reach us since the Big Bang. If you could freeze the universe right now and measure outward in every direction, that's how far you could see. 46.5 billion light years to the edge of everything observable. But here's what that number really means. It's not just the limit of what we've seen so far. It's not a technological barrier we might overcome with better telescopes. It's a fundamental boundary called the cosmic horizon. Beyond it, there's more universe, probably much more, but we can never observe it. Not because our instruments aren't good enough, because the light from those regions will never reach us. There are two horizons worth understanding. The first is the particle horizon. That's the boundary beyond which light hasn't had time to reach us yet since the universe began. Given enough time, light from just beyond that boundary would eventually arrive. But there's a second horizon, the event horizon, also called the cosmic horizon. This one is permanent. The universe isn't just expanding, it's accelerating. Regions of space beyond a certain distance are receding from us faster than light can travel through the expanding space between us. Events happening there right now will never causally affect us. Signals sent from there will never arrive. Light leaving those regions in our direction will travel forever and never get closer. The expansion carries it away faster than it approaches. This is the surprise that breaks most people's intuition. There are galaxies out there, right now, that are not just too far to visit. They're too far to ever observe, even in principle, even given infinite time, even if we built a telescope the size of a solar system and waited until the last star died. Those galaxies are fundamentally, permanently, irreversibly beyond knowledge. There might be trillions of galaxies beyond our cosmic horizon. There might be civilizations there. They might be aiming signals at us right now, powerful enough to cross intergalactic space. Those signals will never arrive, not because they're too weak, because the fabric of space itself is expanding faster than the signal can cross it. If they could see us, we'd be beyond their horizon too, two bubbles in an infinite ocean, both knowing the ocean continues, neither able to reach the other. The cosmic horizon isn't like the horizon on Earth, where you can walk far enough to see what's beyond it. It's like being inside a bubble in an infinite ocean. You can see to the bubble's edge. You know the ocean continues beyond it, but you can never reach beyond that edge no matter how fast you swim. Not because you're too slow, but because the bubble itself is expanding faster than you can cross it. There is ocean beyond your bubble. There might be other bubbles, other observers, other civilizations, but they are permanently, irreversibly, fundamentally beyond reach, not just beyond travel, beyond knowledge. Their existence and yours will never intersect, even if both last forever. And the volume beyond our horizon is growing. Every second, more space slips across that boundary. Galaxies we can see today will, in the far future, recede beyond the cosmic horizon. Their light will stretch, redshift, fade, and then they'll be gone. Not destroyed, just unreachable. The universe we can observe is shrinking in terms of what remains accessible. Remember those photons from the beginning? The ones that left Jade's GSZ 14-0 before Earth had oxygen? They almost didn't make it. If they'd started their journey just a bit farther away, or if the universe had expanded just slightly faster, they'd still be traveling and would never arrive. We exist in a narrow window, late enough that complex structure exists to observe, early enough that we can still see the distant universe before it recedes beyond the horizon, forever. We're lucky, not special, just lucky in our timing. Some inflation models suggest the observable universe represents less than 1% of the total universe, less than 1%. The rest is beyond the cosmic horizon, permanently beyond reach, permanently beyond knowledge. There could be infinite universe out there. There could be regions with different physical constants, different laws, different outcomes. We'll never know. This is the final wound. Not that we're not the center, not that we're not special, but that we're isolated, surrounded by a universe we can never access, trapped in a bubble of observability. The cosmos extends in all directions, possibly forever, and we can only ever know this tiny fraction of it, this island of light in an ocean we can't cross. If you enjoyed this, consider subscribing for more explorations like this one. Out there, beyond the edge we can see, the universe continues. It always will, and we'll never know what's there.